I'm recording. What I want to do is to solve this problem. I think it's 31, or it should be. If it's page 165, we have 30 problems, just application of Mohr Circle, and there are some others where you have to calculate the bending moment, shear stress due to torsion, and draw a Mohr circle. So this problem, which is 31 to my numbering here, it says refer to figure 320, which is page 107. 107, this one. And for a shaft aligned with the shaft aligned with the x-axis, create a stress element at the bottom of the shaft just to the left of section B, then draw the Mohr circle for that element. Use D equals 0.5 inches. Okay, to the left section B. So the torque is resisted by this support at A, and we have this load force 60 pounds, and we're going to experience for the ABC section of the shaft, we're going to experience bending as well as torsion. Now the problem is analyzed here in the book, although we could go through the steps at least to where we show the load diagram. So let me represent this shaft. So we have a support here, and again this is the one that's taking the torque, resisting the torque, and then we have the L piece and the down force 60 pounds. I'm probably better off with a finer marker, maybe this one, or Sharpie. So there's A, I have B, and there's C, and these are 3 inches. I have 5 inches, there's 6 inches, and there's 4 inches. Okay. All right, so if I am to move this 60-pound force from here to this point, it'll be the same 60 pounds, but because of this displacement, I'm introducing a bending moment that is equal to 60 times 3 inches. 3, that's 180 pound-inch. And now if I take this force and move it instead here, 60 pounds stays the same. Then I need to also introduce a torque about the axis of the shaft, which is x-axis. I have x here, z is vertical, and there's the y-axis. Okay, so how big is this torque? This torque is equal to 60 times 5, and that's 300 pound-inch. Okay, So now we can draw the load diagram for the ABC section of the shaft, and it's going to be a 2D view looking from, so this is your eye looking this way. So I have, let's see, point A, I have point B, and point C, again 6 inches and 4 inches. The down force 60 pounds. And then we have, remember we have this 180 pound-inch moment, concentrating moment here, 180 pound-inch, okay? In addition, this portion of the shaft is twisted, so because the torque is resisted at A, I have this portion of the shaft torsion. I'm going to show it here. Okay, so we've got the load diagram, same as in the book. Okay. So this was your eye looking at this view, and to find reaction A, we're going to sum moments about C. So sum of moments about C is 0. So what do we have? And we're assuming, again, arbitrarily positive moments for this summation only, to be counterclockwise. So what do we have? We have RA times 6 plus 4, it's 10, and it's going to be negative because it's causing a clockwise versus positive being counterclockwise moment. And then I have positive 180, and then I have positive 60 times 4 equals 0. So RA is going to be 180 plus 60 times 4 over 10. All right, so that's 18 plus 24. It's 42 pounds. Is it confirmed? Yes. I'm checking against the solved problem in the book. All right, so for reaction at C now, I'm summing moments about A, and what do we write? It's going to be so positive 60 times 6, or rather negative. So again, I have the 60 pound force is creating a clockwise moment, so that's negative, plus 180, and then negative, or the positive RC, the way it's shown, RC times full length is 10. Okay, so from here we're at coming back up where I left it, like a open question. So RC is going to be 60 times 6 minus 180 over 10, and this is equal to 36 minus 18, and that's 18 pound-inch, which is same as in the book. Now that we have these figured out, RA again is 42 pound and RC is 18 pound. we can draw the shear diagram. 42 drop by 60 goes to -18. So 42, this is the V diagram in pounds. And then so positive and -18. And this for the bending moment diagram. So at B, this is the one that we're after, so moment, and this is pound inch. So right before B, the moment is going to be 42 times 6. And that's equal to 42 times 6 equals 252. 252. Now we have a counterclock moment that's applied at B, and that's going to cause a drop by 180. So this piece is 252 minus 180, and this is equal to 72 pounds. Let's see, to confirm, it should be 252 minus 180, it's 72. So we have the moment diagram, we have the maximum, or at B and to the left, or at B left, I don't know, B minus, B plus would be to the right, B left. We have, and it says the problem, by the way, it says to analyze a section of the shaft that is below. I'm going to the problem statement. It says bottom of the shaft just to the left of section B. So bottom of the shaft would be, if I'm to show this magnified, just that area of the shaft. So anyway, okay, so it'll be, this is point B, and we're talking about an element that's at the bottom and right before B. So what we're seeing here, we're seeing tensile stress. So for a reason, they advised us to look at that element and not the top one. So we have the element and we have tensile stress caused by this moment, 252, the bigger one, 252 pound inch. And then in addition, just looking at the figure, so we have the long portion holding, and due to the force, 60 pound force, or the torque being transmitted from B to A, I have a I have a sliding, so there's a tau. And what's the sign of tau? This is tau. So again, this is sigma x, and I have tau. It's intersecting the x-axis, and it's in the direction of y, shear stress. Of course, once I know that one of the shear stresses, I can complete the diagram. I know they are head to head, tail to tail. So this is going to be tau. It's intersecting y, tau y. This is tau y x. And then towards it in a way. Okay. All right. So we need to decide how we're going to look at this element. Usually go from below. So this was the eye that was looking at this perspective view. Looking from below, so I'll have the eye looking from below. So this is how light enters the eye. Okay. So I'm going to show the stress element viewed from below. From below. Okay. So stress element viewed from below. I have sigma x. Okay. And then I had the other stresses. I held myself a little bit by looking from below through transparencies, but the reference frame or the axis would be, I use green early, so it would be x in this direction. There will be y going up, and as I rotate x towards y, z is getting into the element, which is the way it's on the actual figure. Okay, so I'm looking from below. I see x to my left, y up, z is going, it's a right hand reference system. If I rotate x towards y and I use the right hand screw, so x toward, I rotate and it goes, I say the right thing? Maybe I need to back off a little bit from the orientation of these axes. So definitely x is to the right. And I'm seeing indeed y up, and I rotate x towards y. Oh. So page is 107. Okay, this was it. So their reference frame is not the right hand frame. So if you rotate x towards y, you'd be advancing down, not up. So this is a wrong reference, or a left hand reference frame. Less of an issue. Let's stay with what we have. X to the right, y up. We had of the shear stresses, we had one figured out, and that was the this one. So this is tau xy. I have tau xy. This is tau yx, and this is tau yx. Okay, so let's calculate. We're left with getting some numbers here. So what is sigma x equal to? Sigma x is going to be the bending moment m over section modulus. We have the diameter of the shaft is 0.5 inches. I'm using not the flexure, the MC over I, but rather I'm using the section modulus version of the equation for a solid round. S is equal to pi diameter power 3 over 32. So this is appendix 1 on page 782. So I have moment, maximum moment. We calculated again 252, and I'm back to that bad black marker over. Again, would be pi times diameter. It's 0.5 at power 3 over 32. Okay. So the numbers are 252, over pi times 32 over 0.5 at power 3. Okay, so this is 20535 psi. Okay, so one more time, power 3 equals times pi over 32 equals, take the inverse times 252. Okay, so I have sigma x, and now for tau xy, let's use torque over section modulus, or polar section modulus, the z value, and again the same appendix. You know, I'm not trying to memorize these, so it's pi diameter power 3 over 16. Torque, we've got the torque, it's 300 pound-inch, as we did the analysis, 300 pound-inch. It's twisting the shaft, the portion AB of the shaft, the 300 pound over, we said, polar section modulus is pi diameter power 3 over 16, and we have 0.5 power 3 times pi over 16. I take the inverse and multiply by 300. So it's 4.95, easily 1885 psi shear stress. Okay. All right, so we have the two stresses, and we can proceed and draw the Mohr circle. For Mohr circle, remember I told you to bookmark one figure, and the figure is this one, 412. I don't think I can pause this, or can I? I may have to. So what do we have? We have I hear a child calling mama, and I'm the one closest to him. Let's see. The child stopped. By the way, it's 10:47 p.m. Okay, so this is sigma, this is tau, and it's clockwise. Should be on at scale. In case of an exam you receive from me, graphing paper. Okay, so on this figure, what do we have for A? Well, firstly, the center of the Mohr circle is sigma average, and sigma average, it's equal to sigma x plus sigma y divided by 2. Sigma y, we have it 0, so it's going to be sigma x 20535 plus 0 divided by 2, and this is 20535 or 2 equals 10267.5 sigma average. This is where the center of the circle of Mohr circle goes. Okay, and then I have the B value, or rather A, we started with A. So A value is sigma x minus sigma average. And because sigma is 0, this is also 10267.5. And B value, it's going to be tau xy. So B value is tau xy, and it's 1885 psi, or psi. Okay. So Mohr circle, it's going to also radius of the circle, which is tau max. Radius of the circle is going to be a squared plus b squared. So I have square rooted. So I have 1026267.5 squared plus 1885 squared equals, and I take the square root, and this is again the radius 10439, also equals to tau max. So I can draw the circle. Alright, so this is sigma 0, sigma average, and I have the two diameter points. The circle also passes through their mirror points, and okay, so this would be sigma 1. I have sigma 2 equals 0, and I have sigma 3. Okay, so what is sigma 1 equal to? Use more paper. Get more paper. So sigma 1 is going to be center of the circle average plus the radius of the circle. So I have 10,267.5 plus 10,439. Sigma 2 again is 0. Sigma 3 is going to be sigma average minus the radius of the circle. So 10267.5 negative 10439. And these are respectively 10267.5. Put in the memory, I'll need it again, plus 10439. 9 equals, this is 20,706.5 psi, and the other value is 39 equals small negative value compared to the other ones, negative 171.5 psi. Okay, child crying. Let me close the door. Okay, so we have principal stresses, sigma 1, sigma 2, sigma 3, and then tau max. It's the radius of the circle. We've got that also. One thing of interest could be what's the angle made by the axis of the pipe with the principal element, and we're looking here. So 2 phi is going to be this angle, 2 phi, and it's going to be arctangent of B over A that we've got. So arctangent of B was 1,885 and A was 10,267.5. Okay, so phi would be half of this value. All right, so 1,885 over 1,0267.5 equals arctangent divided by 2. It's 5.2 degrees. Okay, so 5.2 degrees. And this is the answer. In case we care. More significant are the principal stresses. So answer as well as this one. We could draw a 3D circle. Doesn't bring much information here. And sorry for not pointing, they're more like lemons. So more lemons versus more circles. Doesn't bring additional value to the analysis because tau max occurs on the original 2D circle. All right, well, this being said, I'm going to stop recording and